Nearly 400 million years ago, something grew on Earth that had never existed before. A tree. Step onto the land at that moment and the continents look unrecognizable. The air sits thick and hot around you, and the horizon is dominated by a shape nothing alive today quite matches. No oaks, no pines, no maples, just an alien architecture of green rising for the first time into a true canopy, among the very first forests the planet had ever seen, vast, silent, and about to change everything beneath them and above them. And then, in a geological eye blink, they were gone. Every one of these pioneering ecosystems disappeared from the face of the planet. Paleobotanists spent decades treating this as one of the field's great unsolved mysteries. Recent research has finally cracked it open, and the answer turns out to be stranger and far more complex than anyone expected. There was no asteroid here. No sudden volcanic apocalypse. What killed these forests was something stranger: their own success. This is a story about biological ambition, a climate that transformed underneath them, and an evolutionary triumph that backfired into a global crisis. To understand why, we need to look closely at the strange organism that built these forests in the first place, a genus called Archaeopteris. It thrived during the Late Devonian, and most paleobotanists consider it one of the earliest true trees on Earth. Everything that came before it was low, soft-stemmed, and unimpressive by comparison. Archaeopteris was different. It grew a genuine wooden trunk and a root system massive enough to anchor a giant, and some specimens reached 30 meters tall, roughly the height of a mature oak today. It spread across huge stretches of the two supercontinents of the day, Euramerica and Gondwana, thriving in wet lowlands and along the banks of ancient rivers. Seeds and flowers didn't exist yet, so Archaeopteris reproduced the way ferns still do, by releasing millions of tiny spores into the wind and letting chance carry them to fertile ground. That strategy worked almost too well. Archaeopteris spread across the globe fast, throwing up dense canopies that changed the climate at ground level wherever it took root. For the first time in the planet's history, the forest floor sat in shade instead of direct sun. Damp, sheltered pockets opened up beneath the trees, and an entirely new understory of primitive plants and early land invertebrates moved in to fill them. Here's the twist. The same features that made Archaeopteris so successful were quietly setting up its downfall. These trees carried a genuinely new kind of root system, one that could plunge far deeper into the ground than anything before it. As the trees grew, those roots started tearing the bedrock apart underneath them. That physical fracturing sped up chemical weathering to a scale the planet had never dealt with before. The root systems dissolved minerals straight out of the rock, pulling nutrients loose and flooding the soil with calcium and magnesium. That shift in soil chemistry reacted with the atmosphere above it, and a slow chain reaction began, one that would eventually rewrite the planet's climate. All that weathering sent enormous quantities of nutrients, phosphorus especially, pouring into the rivers of the Devonian world. Rivers carried it downstream into the shallow seas, and the oceans had never seen an influx of nutrients like it. What followed is a process scientists call eutrophication, and on this scale, it turned catastrophic. In the warm Devonian seas, that surplus of nutrients fed colossal algal blooms until the water itself choked on them. Billions of microorganisms died at once, and as they decomposed, they burned through nearly all the dissolved oxygen in the water. Vast dead zones spread across the ocean floor. Many researchers now believe this was a primary driver of the Kellwasser Event, one of the most devastating extinctions in marine history. The oceans weren't the only thing in crisis. Up in the atmosphere, the forests themselves were quietly causing a second disaster just by existing. Archaeopteris and its contemporaries needed staggering amounts of carbon dioxide to build and feed their massive wooden bodies, and they pulled it in constantly through their leaves and photosynthetic bark. Estimates vary, but researchers studying Devonian climate think atmospheric carbon dioxide fell by as much as 80% over this period, one of the steepest drawdowns in Earth's history. Carbon dioxide is what traps the sun's heat in the atmosphere, so a drop that steep effectively stripped the planet of its thermal blanket. Global temperatures started falling, and they fell hard. The planet dropped into a severe, extended period of global cooling and glaciation, and it happened fast by geological standards. That icy shift turned around and struck a fatal blow against the very forests that had triggered it. Archaeopteris and its relatives were specialists. They needed warm, tropical, reliably humid conditions to survive and reproduce, and the world they'd built no longer offered that. As ice sheets crept outward from the poles and the climate turned arid and cold, the damp floodplains these trees depended on started drying up and freezing over. Archaeopteris and its forests had, in effect, engineered their own trap. They'd changed the atmosphere so completely that the exact environment they needed to survive simply stopped existing. When the Devonian gave way to the Carboniferous, the collapse of these pioneering forests cleared space for a completely new generation of plants. Whatever replaced Archaeopteris had to adapt to a radically different world than the one it grew up in, one with far less carbon dioxide and a much more seasonal climate. That transition produced the coal swamps we now recognize from textbooks, dominated by scale trees like Lepidodendron and towering horsetails called calamites, plants that survived by playing an entirely different evolutionary game. And when scientists study the fossilized remains of Archaeopteris today, they're essentially looking at the blueprint for modern plant anatomy. The wooden architecture, the deep root structures, all of it traces back to these ancient giants. What happened to these early forests says something important about the balance between life and the planet that hosts it. Vegetation was never just scenery in Earth's history. It's an active, powerful force, one capable of reshaping an entire atmosphere, an entire ocean, an entire climate, whether it means to or not. These trees didn't disappear because they failed. They disappeared because they succeeded too completely, rewriting the rules of the global ecosystem faster than evolution could keep up. Today, in the quiet fossil beds where Archaeopteris now rests, there's a reminder written into the rock. The biosphere and the atmosphere are tangled together far more tightly than they look, and the balance between them can shift faster than anything living can adapt to it.